Welcome to the lecture of material science. Today we are going to move to a new topic. As usual, before we move to a new topic, let's have a quick recall what we have learned at chapter 2. Chapter 2, we learned there are two types of bonding. The first type is called primary bond. Second type is secondary bond. And there are three primary bonds. They are ionic bond, which is non-directional bond. The second one is covalent bond, which is directional bond. The third one is magnetic bond, which is non-directional bond. And I'm sure you are all aware of these bondings. The secondary bond, there's only one, which is van der Waals bond. Okay, and the van der Waals bond is derived from three kinds of interaction. The one is called induced dipole, right? So we call induced dipole bonds, which is also we call permanent dipole bonds. The second one is induced dipole bond. Okay, and the third one is fluctuated induced dipole bonds, or we also call London dispersion force, right? Fluctuating force. Okay, so in terms of energy, we also know that the bonding is stronger in the primary bond in compared to the secondary bond. The secondary bond, normally the bonding energy is about below 0.1, is about 0.1 electron volt. However, we have a special case, which is a hydrogen bond, right? Hydrogen bonding is the hydrogen energy of hydrogen bond is very strong compared to the normal van der Waals bonds. Okay, they are about 0.252 electron volt. So these are the bondings between atom and between the molecular to molecular, or molecular to atom, or atom to atom. Okay. So this is chapter 2. We already know about the information we want to know, and today we are going to talk about the chapter 3, the structure of crystalline solid. Seems we have problem. Okay, so this is the one. I think in chapter 2 we talk about atoms, and we talk about interaction between two atoms, and then or interaction between two molecules. And chapter 3 we are going to talk about how about interaction between in 1 mole of the molecules or 1 mole of the atoms. So this is the chapter 3 we are going to talk. The first one is the structure of the crystalline solid, and among the structure of the crystalline solid, we know there are 4 types of material. The first type is called metal. Second type is ceramic. Third type is polymer. The fourth type is composite, right? So in order to realize these 4 types of the solid, which is specialized in the crystalline solid, we want to start in the very beginning with the simplest cases. The simplest cases is the metal, because metal has only 1 type of element. Or if we don't talk about alloy has 2 types of elements together, but the pure metal has only 1 type. like the gold, silver. You only have pure gold atoms and get together, it become gold crystal, right? So we want to talk about the simplest case, which is the structure of metals. Okay, and we want to know the crystal structure, and we want to know how to address the crystals. If we look at crystal in different direction, and can we address this direction, or can we address the plane we are looking at? Okay, so we want to know how to address the points in the crystal, the direction in the crystal, and also the plane in the crystal. And in the end, we want to talk about crystal and what are the non-crystals materials. Okay, so this is crystal. Crystal always beautiful, right? So if you want to buy jewelry, the jewelry must be crystal. Expensive jewelry, when you want to engage, when you want to marry, normally you go to a jewelry shop and you buy an expensive ring, right? You buy expensive stuff for the person you want to get married. Right. So how to identify that is crystal? For example, if I show you something like this, this is kind of very pretty stuff I show you here. This is the kind of can we focus this? Can we? Oh, it's very beautiful, right? So is this crystal? Or is this not a crystal? Is this a diamond, I should say? Or is this a plastic? Which one? Can you identify what is this? Well, it looks like very pretty, right? Very pretty stuff. Can we focus? Can we? So how can you identify this is a very expensive diamond or this is a very cheap piece of plastic? Which one? Let me see that? Very good, very good. In United States, most of the high school use this kind of stuff. They want to, they don't use very heavy or very expensive stuff. This is very cheap. It's a kind of USB. How can I make it big? Let me see. Nice. Good, good. Okay. Right. Full screen. It's full screen, right? Okay. Okay, so one of the methods one of the methods to identify whether this is the one I holding in my hand is a crystal or is a non-crystal plastic is the XRD technique. We call X-ray diffraction technique. So if you put this, if you put this piece of material in front of the X-ray, if you put it here, and then if an X-ray beam shoot the crystal, and this crystal, this diffraction pattern make a diffraction beam make a pattern like this, then we will say that, well, the one I'm holding in my hand is the crystal. Why? Because crystal has a repeated unit in 3 dimensions. Okay, so you can see the pattern on the back of this photographic film, a kind of pattern here. If you see nothing on the screen here, then you will say that this material is a non-crystal. So if I say that, well, is this a diamond or this is a plastic, then if you see no pattern here, you will say that, well, this is a kind of piece of plastic. Okay, so this is a kind of technique for the X-ray, using X-ray diffraction. Right. So not only X-ray can form a crystal, can make a pattern, but also electron, right? I hope you still remember. The photon can behave like a particle as well as a wave. Okay, and an electron can behave like a wave as well as a particle. So when electron beam shoot an object and then went through a object and then make a pattern, something like this, then you will realize this is a type of crystal. So for example, this one is a electron diffraction pattern of the germanium arsenide. Gallium arsenide is a semiconductor, a compound semiconductor, right? Hope you remember when we talk about the band gap engineering. This is kind of pattern. So the direction, the distance and the angle can identify this is what type of material and also which direction you are looking at. For example, so that the brightest spot near the center is produced, this one, by the instant direct electron beams. So if you have electron beam shoot in this direction, this is the center, okay? And which is parallel to a 110 crystallographic direction. What does that mean, 110? 110 is kind of a direction of this crystal. So as I just told you, we want to address the point, the direction, and the plane in a crystal. So when the beam is in this direction and you put this crystal in different direction, in different location, in different angle, you will get different patterns. And with this, in this case, you can identify which crystal plane it was presented. Okay. So each of other white spots result from the electron beam that is diffracted by a specific set of the crystallographic planes. So this is a specific graphic planes, which is we call 110. And this material was identified as a gallium arsenide. Okay, so let's start the introduction. So the second one is the fundamental concepts. So if we want to know what is crystal, first of all, we need to know what is non-crystal and what is crystal. So when you see the crystal, that means the atom packed very well in three directional orders. And this one, there's no order. You know that the atom packed not in a good manner. There are some empty space here, and they don't pack in a good direction. So this is called non-crystal, or somehow we call amorphous. And this is what we call crystal. So the definition of the crystal is that atoms are situated in a repeating or periodic arrays, okay, over large atomic distance in a repetitive three-dimensional patterns. So remember, you had to go to three-dimensional x-axis, y-axis, and z-axis, in which each atom is bounded to its nearest neighbor atoms. So this atom is bounded with its nearest atoms. Nearest, okay? So they have bounds. Right. So now, once we know the crystal, and then let's go a little bit detail about the crystal structure. What is the crystal structure? There is extremely large numbers of different crystal structure. There are many type of different crystal structure. You know, when we talk about metal, there are many different types. And we talk about ceramic, they are more complicated. Okay, so there are many different type of crystal structures. However, we talk about the crystal structure in most simple way in the very beginning. The description of the crystalline structure is that how do you describe the crystal structure? You can use atomic hard sphere model. This is called atomic hard sphere model. Okay, you regard atom as a sphere. It can be a silver sphere, it can be a gold sphere, it can be a platinum sphere. Or we use reduced sphere unit cell. This is called reduced unit cell. You know, the atom doesn't represent a very the big one, and we call reduced sphere unit cell. This is reduced sphere unit cell. And next one, we want to know what is lattice. The definition of lattice is that used in a context of the crystal structure. We call this crystal lattice. You know, you have this is unit, right? Unit. And you repeat the unit. And between the unit this is lattice. Lattice. So lattice is also a three-dimensional arrays of the points coinciding with the atom positions. Okay, this is called lattice. So here is the one of the example. We call it face center cubic crystal structure. What is face center? This is a sphere model, right? Hard sphere model. So all the atoms are packed very well closely to each other in this unit cell. And second one, this is called what? This is called a reduced sphere unit cell. This is easy for you to draw by your hand, right? This is not easy. So you can easily to draw a picture like this. In your final exam, if I ask you to draw a reduced, I ask you to draw a face center cubic crystal structure using a reduced sphere unit cell, and this is the answer you need to give me. Okay, and this is lattice, and aggregate of many atoms. So for the unit cell, you have many unit cells, and this is called aggregate of the atoms. How about energy? Energy of the crystal and the non-crystal structure. You know, for a non-dense random packing, and this is the energy between two atoms, right? And I'm sure you are very aware of this curve. This is energy, this is distance between two atoms. So for the energy of the non-crystal structure, you will know that it should be this because they have more distance between two atoms, right? So it shouldn't be in the lowest energy. It should be somewhere around here, which is not stable. Okay, so this is the typical neighbor bonding energy here, and this is a typical neighbor bonding length. However, for the dense and older packing, something like this. This is very dense, right? Compared to the density of these two materials, I'm sure you know that this has a higher density compared to this one. So if this is packing very well, so energy will be the lowest energy, which is very stable. So typical neighbor bond length, and this is typical neighbor bond energy here. No problem, right? Because this is non-stable, so this is easy to have a chemical reaction with other materials. So the dense, older packed structures tend to have lower energies. This is for sure because it's stable. It's difficult to take this atom away because the bonding energy is low. I should say bonding energy is high and this reached to the lowest energy level. Okay, so when we understand the crystal structures, and let's take a look of one example is crystal structure and non-crystal structure. This is the crystalline SiO2. You know, crystalline SiO2 is what? It's quartz, right? One of the examples of the crystalline SiO2 is quartz. Okay, so you have you have unit cell, and the unit cell repeat in 3 directions. So this is what we call crystal. So atom packed in periodical 3 direction arrays. And typically you can find this crystal in different type of materials like metal, like ceramics, like some type of polymer. Have you heard about liquid crystal? Okay, liquid crystal is one type of polymer, but it's in liquid form, so we call liquid crystal. And this is non-crystalline materials. This is a non-crystalline SiO2. What is this? This is what we call quartz, right? One type of crystalline SiO2 is called quartz. This is what? This is glass. The glass you use like this is glass, right? It's non-crystal. Okay? Non-crystalline SiO2. So atom has no, compared to the periodical packing, this is not a non-periodic packing. And occur on complex structures, rapid cooling. You know, when you do the rapid cooling of a material, you will form a non-crystal structure. Somehow, however, we use amorphous instead of non-crystalline. So when you see amorphous, that means it's a non-crystal material. Right. Next topic is unit cell. So what is a unit cell? Unit cell, the crystal structure is subdivided into small repeat entities. So this is unit cell, the smallest unit. You cannot reduce more because this is the smallest repeat unit. You can repeat in 3 dimensions. So for most crystal structures, the cells are parallel pipettes or prism and having 3 sets of the parallel faces. So you have 3 sets. There are 6 faces, right? For this cubic, there are 6 faces, and then you divide it into 3 sets of the parallel faces. The top and bottom 1 set, right, left 2 sets, set 2, front, back 3, set 3. Okay. So the base structural unit is this is the base structural unit. So the convenient usually indicate that the parallelepiped corners coincide with centers of these half sphere atoms. So this is, you have corners, right? This unit cell, you have corners, and you have 8 corners here. So you have 1 sphere in the 8 corners, something like this. So more than a single cell may be chosen for a particular crystal structure. For some cases, you choose 4 unit cells to explain something. Right. This might be in your midterm exam. This might be in your final exam or in Kahoot. So can you find 2-dimensional repeat unit from these figures for me? For example, this is a unit cell, right? This is the smallest unit cell. This is the unit cell which is the smallest repeated unit. As you can see, this can go to this side and go to this side and go to this side. And it repeat. And this is what we call repeat unit. For the 3-dimensional explanation, we call unit cell. In terms of the crystal, we call it unit cell in 3-dimensional. But 2-dimensional, this we can call it repeat unit. So this is a repeat unit, right? How about this one? Can you tell me where is the repeat unit? And how about this one? Okay, please find out for me. How about this one? What I want to tell you is repeat unit doesn't need to always to be square. It can be something like this. It can be something like this, as long as you can repeat. Okay, you can have a repeat the unit. How about this one? Okay, you know, I want you to find out this repeat unit so you know the meaning of the unit cell. But I just want to tell you there's no repeat unit in this paper, in this pattern. Why? Because this is pentagon. Pentagon has no repeat unit. You cannot form a repeat unit with this pentagon. But you can make repeat unit with this picture, and you can make repeat unit with this picture too. Okay, so now let's go to the section 3.4, metallic crystal structures. So what are the material? What is the metallic crystal structure? We know that the bonding is of metallic bonding is a non-directional bonding. So types of the crystal structures for most of the common metals can be, there are 4 types. We want to introduce you here. The first one is called simple cubic structure. We use SC for short. The second one is face center cubic structure. The third one is body center cubic structure. And the fourth one is hexagonal close pack structure. And we use FCC for face centered cubic, BCC for body centered cubic, HCP for hexagonal close pack. Right, so these crystal structures found for many metals has a unique cell of the cubic geometry. Cubic means what? Cubic means that you have the same length of the in X direction, Y direction, and Z direction. That's why we call cubic geometry. But somehow it's not necessary to have the equal length of the in the X direction, Y direction, and Z direction. That's another story. But now we want to talk about the simplest case. So we use a cubic geometry to explain what are the unique cells and what are the lattice. So first example is called simple cubic structure. So this is called simple cubic structure. So you have a cubic structure like this, and you put 8 atoms in the corner of this unique cell. And this is what we call simple cubic structure. Simple cubic structure, okay? This is hard sphere model. This is reduced sphere model, right? Okay? And if you want to use really a unique cell, it looks like this. It looks like this. And this is lattice. You repeat this unique cell in 3 dimensions. So close pack directions are cubic edge. This close pack. When we talk about direction, this close pack direction is this. This is called close pack direction. This is not close pack direction. This direction is not close pack because there's distance between what? Between 2 atoms. Okay, so this is called close pack direction. And this is what we call cube edge. Right, so the first term I want you to remember is called coordination number. This is unique cell, and there's one important term is coordination number. Coordination number, what's the definition of coordination number? Coordination number means the nearest bounding, nearest, how many atoms near the, which is nearest near the atom you want to address. For example, if you use this red sphere here, and there are 6 atoms which are which are most the nearest or closest to these atoms. They are this one, this one, this one, this one, this one, and this one. So if you take this out, so the coordination number for this atom is 6. So there are 6 atoms which are closest to this atom. So that's what we call coordination number. Not only for this one, but also for this one, there are 6, 6, 6, 6. The coordination number, they are all 6. This is the what we call coordination number. Okay, please remember this. This will be in your final exam. So once we know the second term we want to understand is called atomic packing factor. We use APF. APF. What is atomic packing factor? The definition of atomic packing factor is that the value of the unit cell. Okay, and so the value of the atoms in the unit cell divided by value of the unit cell. So you want to know this is a simple cubic structure, right? So APF is that the value of the value of the atoms in this unit cell divided by value of the unit cell. So the important thing is you need to know the edge length or length of the edge of this cube. And also you need to know the radius of this sphere, right? So for example, this is the length of the edge, okay? Or we call edge length. And A is the edge length. R is called radius of the sphere. And in the case of this, R is 0.5A, right? Okay, so let's calculate what's the APF. Of course, you know this is the close pack direction. This is not, okay? This is the close pack direction. Right, so what's the APF? For A, here is A power 3, right? So A times A times A power 3. How about the value of the atoms in the unit? How many atoms in this? So value of the atoms in the unit cell. You know how to calculate a sphere, right? And how many atoms in this unit cell? How many? A1, B2, C3, D4. How many atoms in this unit cell? 1, right? Because you have atoms in this edge, 8 atoms in the A edge, and one edge has 1/8 of the sphere. So that means what? You have 8 atoms, but 8 atoms. You have 8 atoms in the 8 corners, and one atom is occupy only 1/8 of the values in the unit cell. So 8 times 1/8, that will be 1 atoms per unit cell, right? So what you can do is 1 here, this atoms, 1 atoms in the unit cell, and you have times what? The value of the sphere. And I'm sure you know this in your high school, right? 4/3 times pi and 0.5A power 3. Okay, so, and you know that this is R, right? R can replace to 0.5A. So as a result, the answer you can get, this is the value of per atom. So as a result, what you can get is what? 0.5, 0.52. And I'm sure you understand this is a dimensionless quantity because of what? Because value divided by value. So this is a dimensionless quantity. Okay? So I want you to remember this number. This is important, 0.52. Please remember this. And as a matter of fact, this is not difficult at all. You can do the calculation. You don't need to remember very hard because it's easy to do the calculation. Okay, so the first one, you want to know the coordination number. Second one, you want to know the APF. So what the simple cubic structure SC normally is rare because this is not a good packing. Is you know when you have low packing density, in this unit cell you only have 50% occupied by sphere. So another 50% is empty. This is not a good packing. The ideal packing is the atoms pack very well in this unit cell. It must be more than half, right? So 0.5 is not a good packing density. So you cannot find this kind of packing among these metals. So only one case here is called polonium. Okay, has this structure. Only one, not much. Okay, let's take a look of the second case, which is body center cubic structures, crystal structure. And this is called body center. Why we call it body center? Because you have atoms in the 8 corners. So there are 8 atoms in the 8 corners, and you have one atom in the center of this unit cell. So this is called body center. This is body, right? Body center, cubic crystal. And this is the reduced sphere model. This is the hard sphere model. And lattice looks like this. No problem, right? So now let's take a look. Let's find out what's the coordination number and what is the APF. So body center cubic crystal is that a cubic unit cell with atoms located at all 8 corners and what? And a single atoms at the cube center. Right? This is cube center. This is called body centered cubic crystal. So let's find out what are the coordination number. What's the coordination number? Can you tell me? Coordination number. A6, B8, C12, D, sorry, whatever. Of course, it's the answer of whatever, right? Coordination number, how many? Tell me, raise your hand. Yes. A, right? Thank you. 0.5. Piece of cake. Thank you. Right. A, right? 1, 2, 3, 4, 5, 6, 7. There's one behind this picture. 8. This is called coordination number. Piece of cake. Okay, so atoms per unit cell. How many atoms per unit cell? In this cube? A. I think it's too easy. I don't want to insult you, This is too easy. Number 2, right? There are 2 atoms in this unit cell. Why? There are 1/8 of the sphere in the corner, in the 8 corner. So you have 1 like simple cubic, like single cubic structure, and you have 1 whole spheres in the center. That means what? You have 2 atoms per unit cell, right? And then how about the relationship between radius and the H length? Can you tell me? In order to find out APF, you need to know the relationship between radius and the H length, right? So let's find out. This is this is what we want to know. And if you make it as a if we take a top view of this cube, we'll realize that A is this one, and then this is what? Root 2A, right? This is root 3A. And you realize R is what? 4R. 4R. You learned this in your high school, am I right? Or junior high? No problem, right? Must be in junior high. I'm sure my daughter doesn't know this. But anyway, forget about my daughter. Okay, so you realize root 3A is equal to 4R. R is radius. So let's make so A is equal to 4R divided by root 3. No problem. Okay. So let's find out the two important information we want to know here. One is coordination number. The second one is APF, atomic packing factor. So coordination number, you already told me they have eight. The number is 4. The number is 8, right? Okay. So and we also realize the relationship between the edge length and the radius of the atom this is represent the relationship between radius and the edge edge length. So how do you calculate atomic packing factor or BCC? So APF will be A power 3, right? And then on the top, in the bottom is this. On the top, what? There are 2 atoms in this unit cell. And then you want to times what? You want to times the value of a sphere. Of course, you know this is R power 3. But when you know R and 3, the relation between R and 3, R and the H length, and you replace like this, again, this is dimensionless quantity. And when you do the simple calculation, you will realize the answer is 0.68. That means what? That means there are 86% of this unit cell is occupied by atoms. There are another 32 empty space. 32% is the empty space. Okay. So what are these BCC? BCC is in a periodical table group 1. Sorry. So this is number 6 in a periodical table. Number 6, number 5, number 6, and number 1. I don't want you to remember this. Just have a rivalry idea. You just check. Once you need to use this, you just check the periodical table. You just Google. You will find out. So lithium, sodium, potassium, whatever. Number 1, number 5, number 6. Right. The next topic is the phase center cubic crystal structure. Unfortunately, we run out of our time today. Before we need to,